somewhere near Jupiter tonight. If the sky is clear where you are and the planet is above the horizon, you can find it with your eyes alone. Jupiter itself is easy. It does not twinkle the way stars do. It burns steadily, a little colder than a star in color, holding its light, without the nervous shimmer of something at greater distance. Most people who have seen it outdoors on a clear night remember it as the brightest thing that was not the moon, a fixed, patient point that did not behave like the rest of the sky. And orbiting that point, at a distance no unaided eye can separate from the planet's glare, 4 worlds circle in their own slow procession. One of them is roughly the size of Earth's moon. It is covered in water ice. From a distance, it appears almost perfectly white, cleaner and smoother than anything else in the outer solar system, a small sphere so featureless from afar that astronomers who expected to find a cratered, battered surface like so many other moons were briefly confused by what they saw instead. Its diameter is approximately 3,122 kilometers. It completes one orbit around Jupiter every 3.5 days. It has been doing this since before the Earth had oceans of its own. Tonight we are going to spend some time with it, not with the drama that surrounds it in popular descriptions, not with the alarm of a big question held out like a net to catch attention, just with the thing itself, a small icy moon turning slowly around the largest planet in the solar system, carrying something inside it that 4 centuries of looking has only recently begun to read. Its name is Europa, and what lies beneath its surface is an ocean that has existed in total darkness, without any witness, for longer than life has existed on Earth. We begin there, not at the ice, not at the ocean, but at the beginning of noticing. A winter night in Italy. A small instrument pointed toward a bright planet, 4 tiny points of light that were not supposed to move. In January 1610, Galileo Galilei turned a telescope toward Jupiter and saw something that his training told him was impossible. There were points of light near the planet, small, faint, arranged in a line. He assumed they were background stars, the kind that appear in every field of view when you point an instrument at the sky. He noted their positions and moved on. The next night, he looked again. They had moved. Not in the way background stars move, slowly as a group, carried by the rotation of the Earth through the night sky. These points had shifted relative to Jupiter itself. They had changed position in a way that could not be explained by Earth's motion. And on the night after that, they had moved again. Some had disappeared around the edge of the planet. Others had reappeared on the opposite side. Within a week, Galileo understood what he was seeing. These were not stars in the background. They were worlds, 4 separate objects orbiting Jupiter the way the moon orbits Earth. He had never seen anything orbit other than Earth before. Nobody had. The idea that other worlds might move around other centers was not yet part of the available picture. He kept watching. He recorded their positions each night, building a table of where each one appeared, measuring the regularity of their motion. The innermost one completed its circuit fastest. The outermost was slower. The orbits followed rules that he could write down and predict. One of the 4 was Europa. In his notes, it appears as a number, the second object from Jupiter in the system he was cataloguing. He had no way to know its surface was ice. He had no way to know it held an ocean. He saw only that it was there, that it moved, and that its movement was regular enough to map. There is something in that early act of watching that feels genuinely old, not the instruments or the geometry, but the quality of attention itself. A person, alone in the cold, pointing a tube of lenses at a bright object, writing down what they saw, night after night, because the numbers were building towards something they could not yet name. That patience is not a historical artifact. It is the same thing that drives every careful observation that has happened since. The same quiet insistence that what is real is worth recording accurately, even when the meaning is not yet clear. There is a good chance that on some quiet night, driving home late, stepping outside for a moment, standing in a dark backyard, you have looked toward Jupiter without thinking much about it. A bright point, steady, holding its place while everything else wheeled slowly overhead. It does not announce what orbits it. You would have had no particular reason to wonder. Most people who have seen Jupiter in the night sky have passed on without pausing there. But the worlds were always moving. Europa completed its circuit every 3.5 days, day after day, decade after decade, through centuries when no instrument could resolve it from the planet's glare, through periods when no one was watching at all. It kept its orbit through the decades before the first spacecraft was built, through the years before anyone had a word for what lay beneath its surface. It was always there, always moving, carrying its hidden ocean around Jupiter, in the same patient arc it has been tracing since before the first human being stood upright and looked at a night sky. Galileo's act of noticing, writing down 4 moving points, night after night, began a chain of looking that has continued for 400 years. Each generation inherited what the previous one had recorded and looked a little more carefully, a little deeper, with instruments the previous generation could not have imagined. We are somewhere in the middle of that chain, not at the end. What we have found so far is stranger and more consequential than anything Galileo's table of orbital positions suggested was possible. The first spacecraft to photograph Europa closely was Voyager 1 in March 1979. The scientists on the imaging team had expectations. They had already seen what the outer solar system's moons tended to look like. Callisto, the outermost of Jupiter's large moons, was heavily cratered, its surface dark and ancient, every impact preserved in the rock and ice like a record of everything that had ever struck it. Ganymede was similar in character. The assumption, reasonable enough given what had been seen elsewhere, was that Europa would follow the same pattern. A cratered sphere, geologically dead, a fossil of the early solar system. The pictures that came back did not match. Europa's surface was bright, unexpectedly bright, reflecting sunlight with an efficiency that suggested fresh, clean ice, rather than the darkened, processed material that coats older surfaces. And it was smooth, unnervingly smooth. The craters that should have accumulated over 4.5 billion years were nearly absent, where this showed the accumulated record of every rock that had ever struck it. Europa looked almost unmarked. 4 months later, Voyager 2 passed through the Jupiter system on a trajectory that brought it significantly closer to Europa. The images it returned were clearer, and they showed something that had no easy precedent in planetary science at the time. The surface was crisscrossed with lines, not subtle markings, vast features, some of them stretching thousands of kilometers across the face of the moon, thin and sharp, intersecting and overlapping in patterns that looked, in the early descriptions, like the cracked surface of a frozen lake. Double ridges ran in parallel pairs with shallow troughs between them. Broad bands cut across the terrain where the ice appeared to have been pulled apart and filled from below. Patches of rough, jumbled blocks sat beside smooth, unbroken plains. The scarcity of craters was what mattered most. On any airless, geologically inert world, craters accumulate. There is nothing to erase them. They pile up over time, older impacts buried under younger ones, until the surface reads like an archive of everything that has ever struck it. Europa's surface had been almost entirely cleared. Whatever age the ice carried, it was not old. Estimates from the crater count placed the average surface age somewhere between 60 and 90 million years. Young, in geological terms, for a world that has existed for 4.5 billion years. Something kept renewing it. The most natural explanation was that the ice was not fixed, that somewhere beneath the smooth exterior, a process was operating, something that broke the crust, shifted it, and sealed it again, erasing old features and replacing them with new ones. The fracture lines were not cracks in a dead surface. They were the traces of a surface that had been moving. The implication arrived quickly, even in 1979, before any spacecraft had measured Europa's interior. If the surface was young and mobile, the reason was almost certainly liquid, water, somewhere beneath the ice, pressing upward, warm enough to stay fluid. present in quantities large enough to drive the motion of an entire moon's crust over geological time. Europa's surface temperature is approximately -160 degrees Celsius. At that temperature, nothing on the surface could possibly be liquid. The ice is as hard as rock, but temperature at the surface is not the whole story, and what lies beneath it does not follow the same rules. The same light that left Europa tonight and is arriving at telescopes right now carries the same record that the Voyager cameras began reading 45 years ago. The lines are still there. The smooth plains are still there. The surface is still renewing itself, quietly, in the same way it has been since long before anyone pointed a camera at it. The cameras only caught up. What they found when they looked carefully was a surface that was telling a story about what lay below, and the story required water and heat and a process that had been operating for a very long time. The details of that process took another 16 years and an entirely different spacecraft to begin reading properly, but the first chapter had been written in the photographs from 1979. Europa was not a dead world, it was an active one. And whatever was keeping it active was sealed beneath the ice, invisible from above, patient in its darkness, waiting for an instrument sensitive enough to find it. The Galileo spacecraft arrived at Jupiter in December 1995 and spent the next 8 years making close passes through the system, returning data on the moons with instruments the Voyager cameras could not carry. Its most important contribution at Europa came from a magnetometer, a device that measures the strength and direction of magnetic fields. Jupiter has the most powerful magnetic field of any planet in the solar system, roughly 20,000 times stronger than Earth's. This field rotates with Jupiter, which completes one full rotation every 10 hours, sweeping its influence past the orbits of its moons like a slow, powerful beam. Any electrically conductive material caught in the path of that rotating field will respond. Charged particles within a conductor shift in reaction to the changing magnetic environment, generating their own secondary field. This secondary field is called an induced field. It behaves in a specific, predictable way. It varies in strength and orientation as Jupiter's primary field rotates past the inducing body. If you can detect that variation, you can infer that a conductive layer exists, even if you cannot see it directly. The Galileo magnetometer, under the direction of Margaret Kivelson and her team, measured the magnetic environment around Europa during multiple flybys. What they found was exactly this signature. Europa was producing an induced magnetic field that shifted as Jupiter's field rotated. The pattern was consistent and repeatable. It could not be explained by rock, which is not conductive enough. It could not be explained by ice, which is an insulator. The most physically consistent explanation, the one that matched the data across every flyby, from every angle, was a global layer of electrically conductive salt water. An ocean, not a small one, not a pocket or a localized reservoir, a global shell of liquid water wrapping the entire moon beneath the ice, salty enough to carry electrical current, large enough to produce a field that a spacecraft could measure from hundreds of kilometers above the surface. The water is there because Europa is being squeezed. Europa does not orbit Jupiter in a perfect circle. Its orbit is slightly elliptical, and that eccentricity is maintained by a gravitational relationship with two neighboring moons, Io, the innermost large moon, and Ganymede, the third. The three moons are locked in a resonance. For every orbit Ganymede completes around Jupiter, Europa completes exactly 2, and Io completes exactly 4. This resonance keeps Europa's orbit from circularizing, which it would naturally tend to do over time through tidal friction. Instead, the orbit stays slightly elongated. As Europa moves along this elliptical path, its distance from Jupiter changes. When it is closer, Jupiter's gravitational pull is stronger. When it swings farther away, the pull weakens. The variation happens on a cycle of 3.5 days, Europa's orbital period, and it means the entire moon is being flexed. Stretched slightly when it is near, relaxed slightly when it is far, in a rhythm that never stops. This flexing generates heat. not from any external source, and not from radioactive decay in the interior, though that contributes something, primarily from friction, the mechanical resistance of a solid body being deformed repeatedly, the same way a metal rod bent back and forth grows warm at the bend. In Europa's interior, this tidal heating produces enough energy to keep the base of the ice shell at the melting point of salty water, maintaining a liquid ocean beneath frozen surface ice that is at the top far too cold to melt. The ocean has been warm enough to stay liquid for most of the solar system's history. The Laplace resonance that drives tidal heating has been stable for billions of years. Whatever chemistry has been developing in that darkness has had time measured not in decades or centuries, but in geological epochs. The volume of the ocean is difficult to hold as a single thought. Current estimates place it at roughly twice the volume of all of Earth's oceans combined: the Pacific, the Atlantic, the Indian, the Arctic, the Southern. Every cubic meter of salt water on this planet, doubled, contained inside a moon that could fit inside the continental United States, extending in the liquid layer alone somewhere between 60 and 100 kilometers in depth before reaching a rocky seafloor below. And above all of it, the ice. In 2022, the Juno spacecraft, which primarily studies Jupiter itself, made a close flyby of Europa and turned its microwave radiometer toward the moon's surface. Microwave radiation penetrates ice to depths that depend on the ice's temperature, composition, and internal structure. By analyzing how microwaves interacted with the ice shell and returned to the instrument, the team was able to estimate its thickness. Their measurement, published in 2025, placed the shell at approximately 29 kilometers thick, plus or minus 10, 29 kilometers of ice above an ocean that may be 100 kilometers deep. The ice is not clean. The Juno data revealed scattering features in the upper hundreds of meters, evidence of internal structure below the surface, invisible from above, microfractures, pockets of brine where dissolved salts have depressed the freezing point enough to keep small volumes of water liquid inside the ice itself. Voids where tidal flexing has worked gaps into the crystalline structure over millions of years. The shell is not a monolithic slab. It is a mechanically complex layer with internal texture, fractured and porous in ways that matter enormously for what moves through it. Above the seafloor, the water circulates. Warm water rising from contact with the rock below, cold water descending from the base of the ice above. A convective cycle that has been running slowly and continuously for billions of years. This circulation mixes the ocean from floor to ceiling, distributing heat and chemistry throughout the entire liquid volume. Whatever the seafloor produces, the ocean moves. And where the ice has been most recently broken, the ocean's contents reach the surface. Chaos terrain is the name planetary scientists give to regions of Europa's ice where the normal surface patterns have been disrupted. The regular ridges and smooth plains give way to rough, jumbled blocks, sections of ice that appear to have broken free, tilted, drifted, and then frozen again in new positions, like ice flows on a river after a spring thaw. The texture is disordered. The geometry is wrong, in the way that something is wrong when it has been moved and reassembled imperfectly. The leading explanation is that warm material from below, either water or warm ice approaching the melting point, rose toward the surface and destabilized the crust from underneath. The overlying ice thinned, weakened, fractured. Blocks shifted during the disruption. Then the surface refroze, locking the displaced blocks in place. Sailors who crossed the Pacific by starlight had no category for an ocean sealed under ice. The idea itself, water locked in cold darkness, warmed from within by forces operating deep in the interior of a small moon, would have been beyond any framework they carried. But the idea of water holding something precious in the dark, of an ocean whose contents are not immediately visible but present and real, cycling on its own terms beneath what can be seen from above, that is old enough to belong to every tradition that has ever looked at the sea. What the ocean holds, what it has been carrying in its cold circulation for 4 billion years, was the question that the Galileo spacecraft could not answer. The magnetometer found the ocean, the cameras mapped the chaos terrain, but the chemistry of what lay beneath remained for another 2 decades beyond reach. Terra Regio is the largest chaosed region on Europa. It spans roughly 1,800 kilometers across the Moon's leading hemisphere, the side that faces forward along Europa's orbital path. Before 2023, it was known primarily as a geological feature, a place where the ice had been dramatically reworked, where the surface was rough and discolored, brown and tan against the white of the surrounding plains. The Hubble Space Telescope had detected sodium chloride, ordinary table salt, concentrated in Terra Regio. Salt dissolves readily in ocean water. Finding it on the surface, concentrated in disrupted terrain, strongly suggested that salty water from the ocean below had reached the ice above and left its dissolved minerals behind as the water sublimated away. Salt from the ocean deposited on the surface in the one region where the ice had been most recently broken. That was the first chemical link between what lay above and what lay below. It would not be the last. In September 2023, 2 separate research teams published their findings on the same day in the same journal. Both had used the James Webb Space Telescope. Both had pointed it at Europa. Both reached the same conclusion. There was carbon dioxide on the surface of Europa, and it was not where anyone would put it if it had arrived from space. The James Webb Space Telescope orbits the Sun approximately 1.5 million kilometers from Earth at a gravitational balance point where it remains stable and cold, its mirror shielded from sunlight, its instruments tuned to infrared wavelengths, the light of heat and molecular vibration. When infrared light falls on a surface, different molecules absorb and reflect it at different wavelengths. Carbon dioxide absorbs infrared at a specific set of energies, determined by the way its 2 carbon-oxygen bonds stretch and bend. Water ice absorbs at others. Every molecule writes a different signature in the reflected spectrum, a chemical fingerprint readable from across the solar system, if the instrument receiving it is sensitive enough. Webb's near-infrared spectrograph splits incoming light into thousands of individual wavelength channels, each recording how much light arrived at that precise color. The result is not a photograph, it is a chemical inventory, molecule by molecule, pixel by pixel, of what sits on the surface of a world more than 600 million kilometers away. The carbon dioxide Webb detected was concentrated in Terra Regio, not spread evenly across Europa's surface, not clustered at impact sites where meteorites might have delivered carbon from outside the system. Concentrated in the one region already known from Hubble's salt detection to be the place where ocean material reaches the surface most readily, the region where the ice has been most recently broken, the region where the disruption runs deepest. Carbon dioxide is unstable on Europa's surface. Jupiter's radiation environment, the charged particles trapped in Jupiter's magnetic field and swept continuously across the Moon, breaks down carbon dioxide over time, destroying the molecule and converting it to simpler chemical fragments. Any carbon dioxide sitting on an old undisturbed surface would have been degraded away over hundreds of millions of years. The fact that it is present at all in concentrations large enough for Webb to detect means it arrived recently in geological terms. The fact that it is concentrated in geologically young chaos terrain confirms the direction of travel, up through the ice from the ocean below. One team, led by Geronimo Villanueva at NASA's Goddard Space Flight Center, detected 4 distinct spectral features of carbon dioxide ice and found its distribution across the surface correlated with the geological youth of the terrain beneath it. The older the surface, the weaker the carbon dioxide signal. The younger the terrain, the more recently the ice had been broken and refrozen, the stronger the signal. The second team, led by Samantha Trumbo at Cornell University, mapped the carbon dioxide distribution and found it concentrated not only in Terra Regio, but also in portions of another chaos region on the leading hemisphere. More significantly, they noted that the carbon dioxide appeared in the same disrupted terrain where Hubble's sodium chloride had been detected years earlier. Two different molecules, two different instruments, two different research groups, the same locations on the ice. Salt from below, now carbon from below, both concentrated in the places where the ice had been most recently broken. Both teams also measured the carbon isotope ratio in the detected carbon dioxide. Carbon exists in two stable forms, carbon-12 with 6 protons and 6 neutrons, and carbon-13 with 1 additional neutron. The ratio between them can shift depending on the chemical and biological processes a carbon-bearing material has passed through. Villanueva's team measured a carbon-12 to carbon-13 ratio of approximately 83, plus or minus 19. The range is wide enough to overlap with several possible formation scenarios, both biological and otherwise. The isotope data does not confirm life. It does not rule it out. What it provides is a baseline measurement where none existed before. The first number in what will eventually become a more precise chemical portrait of the ocean below. In 2025, a follow-up study by Richard Cartwright and colleagues examined the isotope data in greater detail, focused specifically on Tara Regio. They tested every plausible formation pathway for the detected carbon dioxide: external delivery by meteorite, surface production through radiation chemistry, acting on material from outside the system, and internal delivery from the ocean below. One by one, the external explanations failed to account for the spatial distribution, the chemical form of the detected molecules, or the relationship between carbon dioxide abundance and the geological age of the terrain. The internal explanation accounted for all three. Every road led back to the ocean. Then in 2026, a team applied a technique called spectral decomposition to Webb's observations of Europa's leading hemisphere, breaking the surface signal into separate chemical components and analyzing 9 individual spectral bands covering water ice, carbon dioxide, and other compounds. What they found extended the picture considerably. The carbon dioxide was not confined to Tara Regio. It appeared across multiple chaos terrains on the leading hemisphere, and in each location, it correlated with regions where the ice texture was anomalous, physically altered in ways consistent with disruption and thermal processing. The carbon did not appear randomly. It followed the geology. Wherever the ice had been broken and refrozen, the carbon dioxide signal was present. Wherever the ice was old and undisturbed, the signal weakened or disappeared. The pattern was consistent across independent disruption events, separated by hundreds of kilometers of surface. The ocean was not leaking in one place. It was leaking wherever the crust had been recently opened. Every time the ice broke and healed, the ocean left its mark. Every generation of scientists who has looked at Europa has handed the question forward, slightly more defined, to the next. Galileo recorded 4 moving points. Voyager photographed the cracked surface. Galileo's magnetometer found the ocean's conductive signature. Hubble found the salt. Webb found the carbon. Each instrument gave the following generation a clearer picture to work from and a sharper question to ask. Webb is the latest hand in that chain. And what it found has made the question harder to set down than it has ever been before. The comparison with Saturn's moon Enceladus sharpens this further. Enceladus is small, roughly 500 kilometers in diameter, less than a sixth of Europa's size. But it has something Europa has not yet been confirmed to have: active plumes. In 2005, the Cassini spacecraft detected water vapor erupting from the moon's south pole in jets that rise hundreds of kilometers above the surface and spray material directly into space. Cassini flew through those plumes repeatedly during its 12 years at Saturn, capturing and analyzing whatever the plumes contained. What it found was a chemical portrait of Enceladus's ocean obtained through direct sampling. The plumes carried sodium chloride and sodium bicarbonate, salts indicating prolonged contact between the ocean water and rock. They carried silica nanoparticles only 6 to 9 nanometers across, which on Earth form only in hydrothermal systems where water interacts with rock at temperatures above approximately 90 degrees Celsius. They carried molecular hydrogen, the same chemical fuel produced by the serpentinization reaction, where seawater reacts with iron-rich minerals on a seafloor and releases hydrogen as a byproduct. On Earth, this molecular hydrogen is the primary energy source for microbial communities living at hydrothermal vents in total darkness, far from any sunlight. Enceladus is small. Its ocean is far smaller than Europa's. Its tidal heating is less intense, its water-rock interface less extensive, its geological history shorter, and yet Cassini found molecular hydrogen in its plumes, direct evidence of hydrothermal chemistry operating on its seafloor, producing the same fuel that sustains the deepest ecosystems on Earth. Europa's ocean is vastly larger. Its seafloor interaction has been operating for longer. Its tidal heating has been running continuously, driven by the same Laplace resonance that has remained stable for billions of years. If the conditions on Enceladus's much smaller seafloor are sufficient to produce hydrothermal chemistry, the conditions on Europa's seafloor, larger, older, more energetically maintained, are at least as favorable, and likely more so. Webb cannot fly through a plume. It cannot capture particles the way Cassini could. What Webb can do, and what it has now done, is read the chemical record that the ocean has deposited on the ice above it, molecule by molecule, region by region, with enough precision to determine where the molecules came from and how recently they arrived. Enceladus gave science a taste of ocean world chemistry through direct plume sampling. Europa is giving science a chemical map drawn in carbon and salt on a canvas of fractured ice, assembled one observation window at a time across an ocean world 4 times as large. The map is still being drawn, but the pattern it is revealing has been consistent across every instrument that has contributed to it. The ice holds a record. The record points downward. Europa's ocean has likely been liquid for more than 4 billion years. The Laplace resonance, the gravitational relationship among Io, Europa, and Ganymede that keeps Europa's orbit elliptical and its interior warm, has been stable since the early solar system. The tidal engine has been running continuously, at roughly the same rate, since before the first microorganism appeared on Earth. Whatever chemistry has been developing in that ocean, in that darkness, pressed between kilometers of ice above and kilometers of rock below, has had time that most units of measurement are poorly suited to describe. On Earth, life emerged from chemistry within a few 100 million years of the planet forming stable liquid water. It took another 3 billion years to develop the complexity that eventually produced multicellular organisms. The timescale matters because chemistry, in the presence of the right ingredients and a continuous energy source, does not stand still. It accumulates, it builds, it generates complexity through processes that require no instruction other than thermodynamics and time. Europa's ocean has had both. The rocky seafloor is not a passive surface where ocean water comes into contact with iron-rich silicate minerals, the kind expected in Europa's mantle based on its density and formation history. A cascade of chemical reactions can occur. Water interacts with the minerals, oxidizing the iron and releasing molecular hydrogen as a byproduct. This process, called serpentinization, operates on Earth's ocean floor wherever seawater percolates through newly exposed rock. It produces not only molecular hydrogen, but also conditions that favor the formation of simple carbon-bearing molecules, methane, formic acid, dissolved carbon dioxide, from whatever inorganic carbon the rock contains. Where the seafloor is warm enough, hydrothermal systems can develop. Hot water rises through fractures in the rock, carrying dissolved minerals. When it meets the colder ocean above, it precipitates those minerals and releases whatever gases it carries. On Earth, these hydrothermal vents, discovered for the first time in 1977, the same year that Voyager was launched, support ecosystems that owe nothing to sunlight. Tubeworms, shrimp, bacteria, entire communities of living things drawing their energy from chemical gradients between the hot, mineral-laden water of the vent and the cold, oxygenated water of the surrounding ocean. Whether Europa's seafloor is volcanically active, or whether its water-rock interaction is slower and more diffuse, remains unconfirmed. Europa Clipper will carry instruments capable of detecting the heat signatures and chemical traces that would distinguish between the two. But even the slower scenario, water percolating through porous rock, dissolving minerals, releasing carbon and hydrogen over geological timescales, is enough, given 4 billion years of operation, to have filled the ocean with the chemical building blocks that habitability assessments look for. Carbon is confirmed, arriving at the surface from below. Hydrogen was likely produced at the seafloor through spentonization and dissolved into the ocean. Oxygen and sulfur appear on the surface as radiation products and as material delivered from Io's volcanic activity. Water is the ocean itself. The ingredients are present. Whether they have done anything with each other in 4 billion years of circulating in the dark is the question Europa Clipper is being sent to begin answering. The spacecraft launched on October 14, 2024, carried aboard a SpaceX Falcon Heavy rocket from Kennedy Space Center in Florida. It is the largest planetary mission spacecraft NASA has ever built, more than 30 meters across with its solar arrays deployed, roughly the length of a basketball court, designed to generate the power it needs from sunlight at Jupiter's distance from the Sun. It performed a gravity assist flyby of Mars in March 2025 and will swing past Earth in December 2026, using each planet's gravity to gain speed before heading into the outer solar system. It will enter orbit around Jupiter in April 2030. Once there, it will not orbit Europa directly. Jupiter's radiation belts are too intense for a spacecraft to survive prolonged exposure at Europa's orbital distance. Instead, Europa Clipper will loop through the Jupiter system on a wide trajectory that carries it repeatedly in and out of the radiation zone, making 49 close flybys of Europa over the course of its primary mission. Some of those passes will bring the spacecraft within 25 kilometers of the surface. It carries 9 scientific instruments. A radar system called Reason will send radio waves through the ice and listen for reflections from boundaries within the shell. The ocean ice interface, subsurface liquid pockets, structural changes within the ice. A thermal imager will map surface temperatures at high resolution, looking for warm spots that indicate recent geological activity or thin ice. Magnetometer will examine the surface chemistry across the entire Moon at resolutions hundreds of times finer than Webb can achieve from deep space. A mass spectrometer will analyze any particles the spacecraft passes through, material sputtered off the surface by radiation, or ejected by any plumes that may be active during a flyby. Webb's chemical map, carbon dioxide in chaos terrain, the correlation between volatile enrichment and disrupted ice texture, the spatial pattern that 2026 studies extended across multiple geological features, will tell Europa Clipper's team where to look first. When the spacecraft swoops past Terra Regio, it will do so knowing that Webb detected ocean-sourced carbon there. The radar will probe what lies beneath that specific region of ice. The spectrometer will examine its chemistry at meter-scale resolution. The thermal imager will search for anomalies, indicating that the process that brought carbon to the surface is still operating. Somewhere in 2026, before Europa Clipper reaches Jupiter, before it makes its first close pass, Webb will look at Europa again. The orbital geometry of whatever appeared in the data in August 2024, and the follow-up windows that followed, will either bring the signal back into view or not. That observation window will not resolve everything, but it will add one more data point to a picture that has been building carefully and slowly across 400 years of looking. The ocean does not change between observations. It keeps its chemistry, its heat, its slow convective circulation, indifferent to whether anyone is watching. It has kept these things through every night since Galileo first wrote down 4 moving points of light and did not yet have a word for what they meant. What lies beneath Europa's ice has been there the entire time. The instruments are only now becoming capable of reading it. Galileo saw 4 points of light moving around Jupiter in January 1610. He had no way to know that one of them held an ocean larger than all of Earth's seas combined. He had no way to know that beneath its smooth white surface, a body of liquid water had been circulating in total darkness for longer than multicellular life had existed on this planet. He was watching motion, the regular, predictable arc of 4 small worlds around a large one. And he was writing down numbers. The numbers were what mattered. The meaning of the numbers would take much longer. There is something genuinely peaceful in that, if you let yourself rest in it. Not the ignorance, the continuity. The fact that what Galileo was watching was real, and that it has remained real through every generation since, unchanged by whether anyone was observing it, or what instruments they brought to bear. Europa's ocean was there in 1610. It was there in 1979. When the Voyager cameras photographed the cracked surface without yet knowing what lay beneath it. It was there in 1997 when the magnetometer finally found its conductive signature. It was there in 2023 when Webb read carbon dioxide concentrated in chaos terrain, and 2 independent teams reached the same conclusion on the same day. The ocean does not wait to be discovered, it simply continues. There is a version of every childhood night sky that contained Europa's ocean without anyone knowing. Any clear night when Jupiter was above the horizon and bright enough to notice, and Jupiter is almost always bright enough to notice. The ocean was turning in its darkness, cycling its chemistry, pressing against the underside of its ice ceiling, 400 million miles away. Children who pointed at Jupiter and asked what it was were pointing, without knowing it, at a system that held more liquid water than their entire planet. They were not wrong to find it beautiful. They were just not yet equipped to know how much the beauty contained. This is perhaps what is most worth holding at the quiet end of a long question. The scale of what we do not know is not a failure, it is the condition. Every generation has looked at Europa with the best instruments it possessed and found the same thing, that the instruments were almost, but not quite, adequate to the question. Galileo's telescope was almost adequate to resolve the 4 moons from Jupiter's glare. Voyager's cameras were almost adequate to read the surface geology in full. Galileo's magnetometer was almost adequate to characterize the ocean it had found. Webb is almost adequate to the chemistry of what the ocean contains. In each case, almost was enough to push the question forward. Almost adequate is what progress looks like, most of the time. An instrument that reaches just far enough to find the edge of the next unknown. Europa Clipper will be almost adequate, too, in its own way. It will answer questions that Webb cannot reach. It will find the edges of questions that Europa Clipper itself cannot resolve. And the instruments that follow will find the edges of those. The ocean will remain partially unread through all of it, and that is not a disappointment. It is simply the nature of a question that has 4 billion years of depth. There is a version of this that belongs to everyone who has ever looked up at a clear night sky and felt the particular sensation of scale, not dread, not vertigo, but something quieter, the feeling that the world extends much further than the eye can reach, and that this extension is not threatening but simply true, that the darkness between the bright points is full rather than empty, that a small icy moon, unremarkable in appearance, carries in its interior an ocean whose chemistry is only now beginning to surface. The question has been there as long as the moon has been turning. We have only recently become capable of asking it precisely enough to begin hearing an answer. That is enough for tonight. The rest can wait. In January 1610, Galileo made his first careful record of the 4 points of light moving around Jupiter. He measured their positions each night. He built a table. He noted when one disappeared behind the planet and when it reappeared on the other side. He was not trying to discover an ocean. He was not asking whether anything orbited those points or whether anything lay beneath their surfaces. He was doing what the instruments of his moment allowed, recording the regularity of motion, mapping the system's geometry, writing down what the sky showed when you looked at it carefully and honestly. We are still doing that. The instruments are different. The questions are more precise. The measurement Webb, made in 2023, detecting carbon dioxide in a specific chemical form, concentrated in a specific geological setting, consistent with an internal source, is a different order of sophistication from a table of orbital positions written by candlelight in a Venetian winter. But the underlying act is the same: careful observation, honest recording, a willingness to let the numbers mean what they mean, even when the meaning is incomplete. What 4 centuries of that careful observation have produced is not a complete picture of Europa. It is a picture with depth, layered, built from the contributions of instruments and people, across an unbroken chain of looking. Galileo's 4 points became Voyager's cracked surface. Voyager's cracked surface became Galileo's conductive ocean. The conductive ocean became Hubble's salt, and then Webb's carbon, and then the fractures Juno found reaching hundreds of meters into the ice. Each layer did not replace the one before it. It extended it. The 4 moving points are still the foundation. The orbit is still regular. The moon still completes its circuit every 3.5 days, the same arc it has been tracing since before any human stood upright and looked at a night sky. Europa's ice is still there, smooth over the plains, rough and brown in the chaos terrain, crisscrossed with the long lines that puzzled the Voyager team and have been slowly yielding their meaning ever since. The ocean is still there, turning in its dark, kept warm by the same tidal engine that has been operating since the Laplace resonance locked 3 moons into their orbital relationship billions of years ago. The carbon is still arriving at the surface, in the places where the ice breaks and heals, deposited and then degraded by radiation, replenished again by the next disruption. The chain of looking that Galileo began has not resolved the question. It has clarified it. There is a difference. A resolved question is finished. A clarified question is sharper than it was, better defined, more precisely stated, pointing more directly toward what is still unknown. Europa's question is clarified now in ways it was not a decade ago, and it will be more clarified still when Europa Clipper makes its first closed pass. Whatever the ice holds beneath its surface has been holding it through every generation that has looked up at Jupiter and seen a bright point and wondered, or not wondered, or wondered briefly and moved on. The ocean does not distinguish between those who noticed and those who did not. It simply continues its slow circulation, pressing its chemistry upward through the cracks in the ice, depositing what it carries on the frozen surface above. The act of looking matters, not because the ocean requires it, but because we do. Looking carefully, recording honestly, handing the question forward slightly more defined than we received it. That is what has brought us from 4 moving points to a chemical map of where an ocean touches its own ceiling. Galileo's table of positions is still, in some sense, the first line of that map. The ice is still there. The ocean is still turning. Somewhere in the outer solar system tonight, a small white moon completes another arc around a giant planet. Its surface is nearly featureless from a distance, smooth and bright, a pale sphere holding its light. The long fracture lines that cross it are too fine to see without magnification. The chaos terrain, with its rough brown blocks and disrupted ice, blends into the white at any remove. From far enough away, it looks like nothing in particular, a moon among moons. Beneath that surface, in total darkness, an ocean turns. It presses upward against the ice above it. It carries what the rock below has given it. Carbon, dissolved from minerals, heat from the tidal engine, chemistry that has been circulating for 4 billion years, without pause, without witness, without any interruption that the ice itself could not heal. Where the ice has cracked and refrozen, the ocean has left its mark. Carbon, concentrated in disrupted terrain. Salt, deposited where the water last touched the surface. A record written in molecules on a frozen ceiling, patient and precise, waiting for an instrument sensitive enough to read it. The instruments are coming. Until they arrive, the ocean continues on its own terms, indifferent to the observation windows. indifferent to the spacecraft trajectories, indifferent to everything except the slow chemical logic it has been following since, before the first living thing appeared on Earth. The ice holds. The ocean continues.